Welcome back. In this short video I want to illustrate the relationship between duration, convexity and price approximation. So we already noticed that the relationship between bond prices and yields are not linear. And the shape, so the convexity of this particular curve depends on its second derivative. And we saw that depending on the bond parameters, the convexity can vary quite substantially. Now the issue with that is that if you want to approximate the change of prices just based on duration, you always make an error in this case, and we can just visualize it in this figure. So what happens here is that you have a starting point, P star and Y star, and then you shift the yield by a marginal amount. And depending how significant the shift is, you see of course that the curvature matters more. So convexity really starts playing a major role once you have a more significant change in yield. So put differently, duration is an acceptable proxy of price changes if we only talk about minor changes in yield. But in the case of larger changes, it will be of course affected more and more by convexity, by the fact that the relationship is not really linear. So to understand this relationship more, you see on this slide actually a discussion about a Taylor expansion. So what I want to do now is I want to motivate this using an example and just thinking a bit more carefully about this expansion and why it actually makes sense. Good, let's start with the relationship we try to proxy. Let me just do that and move in here. So I'm looking at a price dimension here, and I have a yield dimension which I denote as R. So that's my yield, that's my price. And it's of course, we know it's not really linear, but we approximate that now using a linear relationship, and we might have a starting value. Yeah, as indicated before, we have a starting value here, and I just denote the starting value as P upper bar and R upper bar, and we know that the true relationship is a convex relationship. Yeah, so now I'm just indicating here this true relationship, and let me just change the color, and we would expect this to be convex, so it bends away from this straight line depending on the level of yield. Good, so if we now start modifying this relationship, so if we want to deviate from the yield and add a small amount, so put differently, if we want to move from this value of yield maybe to this value of yield, and we add here delta R to it, to a new level, this change in yield can be seen as a combination of two different effects. Yeah, first of all, duration of course matters, so you would have a negative impact on price, but then you also see that because of convexity there is a small positive effect. And this combined effect would give you a more precise approximation of a price change. Good, we now move into this argument in a little bit more technical way, going back to a Taylor expansion. Okay, so if we think about this, what we want to do is the following. We want to look at the price of the bonds after adding from the initial value R upper bar delta R to it. Yeah, and we just write here the price is a function of yield. All other parameters are anyway constant in this case. And because it's a price change, I take this minus the initial price at R upper bar. Yeah, so that's our starting point. Now if I look at this relationship, let me just denote this relationship as our first equation. We will get back to this a bit later, so I just want to make sure we mark this appropriately, and we will go back to this in a minute. Okay, so now when I look at the first term, what I want to do is I want to do an Taylor expansion on it, because we know that the relationship between the yield and the price is non-linear. Yeah, so depending on maturity, it can be quite high powers might matter, depending on how many discounted periods you have. So what we can do is we can write this function as follows, as approximately equal to the function assessed at a certain value. So let me just write this as it is, and I want to assess it, so I do again a vertical line. We have seen that before, and here I want to assess it at for very small changes of my delta R, so I just put here R equal to R upper bar. Yeah, so put differently actually in here, so that term here is basically my yield, and this yield is a combination of the initial value and a tiny bit more. Yeah, so if I write R equal to R upper bar, this basically means for very, very small values of delta R. So delta R is very, very, very small. So that's the notation I use. And then of course I go into the first derivative, so I can write this here as dp dr. Again, I would assess all of that at R equal to R upper bar. And then if you remind yourself, it would be x minus a. So in our case, the x would be R minus R upper bar. And then I go into higher orders. So it goes then 1 divided by 2 factorial, which is 2. And then I have the second derivative here, again assessed at R equal to R upper bar. And in here we have our R minus R upper bar power of 2. And then you have here higher orders. And we will see in a minute this is actually delta R power of 3. We have higher orders. Yeah, so that's basically how it looks like. Now if we look at this a bit more carefully, we can start now of course simplifying that. So the first thing we can do is we can just write the following. So this here is P. R is now assessed at R upper bar, so I can just write the following. Then we have our duration, so that part actually would be our duration. And here R is written as R upper bar plus delta R, so this becomes simply my delta R. So a very small change of delta R plus 1/2, and then this is the convexity measure. So that's convexity here. And again, that's assessed at R upper bar, and I get delta X, sorry, X not X. Let me just quickly use the eraser. Oops, that's pretty cool. We get R to the power of 2, much better. And then we have the higher orders. Yeah, so I just squeeze them on the side. Let me just start squeezing this a bit, or move it aside, and let me put here the higher orders of delta R power of 3. Yeah, and they can be of course ignored, because again delta R is relatively small. Of course, the bigger it gets, the more these additional errors matter. But this is basically how we move into the Taylor expansion. Now when we look at equation 1, so if I use now equation 1 and the approximation I obtain here, I of course see that my measure of a price change, so that is the measure of a price change, can be written as follows. So basically from my first equation and using this approximation, I could simply say that delta P, so that's my price change, is approximately my duration. Let me just move that a bit more. It's approximately my duration, assessed at the initial value, times the delta R plus, and then we have the second order term, which refers to the convexity. So that's basically where it comes in, and it goes here power of 2, and then we have some higher order terms we don't care too much about. And we are done. But this basically relates to the stuff you saw on the slide. There is one more thing which you notice. Let me just take a different color for this, and what we basically do is we say that this is roughly dp, and this here is roughly dr, and this here would be dr squared. But this basically implies that I talk about a marginal change, so in the limit this is the case, so in the limit, so for very, very small changes. But that's basically the idea behind it, and what we see is that the more, of course, the more change we have, so the higher the delta R, the more the convexity really matters and will distort our assessment of price changes only based on duration. And of course, in modern applications, you would anyway use numeric methods to account for these effects. But it's important to notice that. Good. I see you in the next.